Continuing with section 4.1, we looked at some vector spaces. Remember, we talked about R2 and Rn, and they will actually satisfy all those 10 axioms. I will show you for R2 maybe later in one of the videos how to show all the axioms or how to work with those axioms in order to verify that the given set is a vector space. So we just saw some vector spaces which consist of vectors actually, but now we will see some examples of vector spaces where the elements or the objects inside are not vectors but can be considered or treated like vectors. So for example, the set of all 2 by 3 matrices with the operation of matrix addition and scalar multiplication is a vector space and is denoted by big M 2 by 3. So whatever the size of the matrix is, we put it under this M for matrix. So for example, the matrix M1, 2 will be 1 row and 2 columns. So all matrices of that size will be a subspace. Actually, in general, any M by N matrix is a vector space. So remember, the matrices in the set will all be of the same order or the same size. So what is the standard addition and scalar multiplication for M 2, 3? I showed you here. If we have two quantities or two matrices from the set M 2, 2, 3. So A matrix is this one and B matrix is this. Then we add components, corresponding components. So we say component wise addition. So first component of the first row, the first column gets added to the first component in the first row and first column, and it gets put on the place which is first row, first column, and so on. And the scalar number or the real number R, when multiplied by a matrix, it gets the whole matrix gets multiplied by that scalar. Next one is the polynomial set of polynomials. So if we have polynomials of, for example, degree 2 or less, this is very important, 2 or less, degree 2 or less, and it is denoted by P sub 2. So this is also a vector space. It satisfies all those 10 axioms. The elements will be of the form Px is equal to A sub 0 plus A1x plus A2x square. Another element, for example, Q of x will be B sub 0 plus B sub 1x plus B sub 2x square. You can also take it like A plus B plus C, and then the next one could be, so you could also say the elements are A plus Bx plus Cx square and then D plus Ex plus Fx square. But that way you only get a finite number of the vectors or finite number of the polynomials. So in general, with the indices, we can write as many as we want. The standard addition and multiplication will be, scalar multiplication will be when you add two polynomials, what happens? We add the corresponding entries or like entries or like terms. So the constant will be added to the constant term. The coefficient of x1, x will be added together, and the coefficients of x square will be added together. So our resulting polynomial is again a second order polynomial. And then scalar multiplication, each term gets multiplied by the scalar. The set of all real valued functions defined on the entire real line is also a vector space and is denoted by this symbol C brackets negative infinity to infinity and bracket closed. So that is the symbol for all continuous functions, real valued continued functions defined on the entire real line. So the addition and scalar multiplication is defined like this. This is our standard one. So basically, mainly these are few of the vector spaces that you will be working with. So we have matrices, we have polynomials, and we have the vectors. So summary of important vector spaces. So these are the ones that you have to remember. That R is a which is the set of all real numbers. So in other words, the line, the real number line, that is a vector space. R2, we mentioned earlier, this is a vector space. R3, the set of all ordered triples, that is a vector space. Basically, the set of all n tuples is a vector space. C minus infinity to infinity, the set of all real valued continuous functions on the defined on the real line is a vector space. CAB, closed interval AB. So these will be the set of all continuous functions defined on the closed interval AB. That is also a vector space. Then P is the set of all polynomials of any degree, all the polynomials, that is a vector space. And then P sub n, which is the set of all polynomials of degree less than or equal to n. So n or lower. So of degree n or degree less than n. So that set is also a vector space. Like we saw P sub 2, we mentioned P sub 2 is a vector space. P sub 3 is a vector space. And so what is this? This will be, P sub 3 will be all the polynomials of degree 3 and less. When the operation of addition and scalar multiplication defined on the set B are not the standard operations, we use the symbols, this one plus circled and for addition, and the dots with inside a circle for the scalar multiplication. So now let us look at some examples of sets that like we have been dealing with or we have seen, or you can imagine, which are not vector spaces. First example is the set of integers. So what are the set of integers will be negative, coming from negative infinity. So negative 3, negative 2, negative 1, 0, 1, 2, 3, dot, 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 dot. So this set is not a vector space. And why is it not a vector space? Because first axiom is to check if two numbers taken from these integers added together give us an integer. That is true. So any integer a plus b will give you an integer c. So this is satisfied. Which one is actually not satisfied, we can directly go to that one. It is the scalar multiplication. So remember, we have to take a integer here. So for example, I can take the integer 2, and if I multiply it with the scalar 1 over 3, so answer will be 2 over 3, which is not an integer. So scalar multiplication, it is, so we say the set is not closed under scalar multiplication, so it is not a vector space. So not closed under scalar multiplication. Therefore, not a vector space. Okay. The set of, next example is the set of second degree polynomials. So notice the difference here. The P2 was the second degree polynomial and lower degrees. But if we just talk about the second degree, only the second degree polynomials, then this is going to fail some axiom or some property of the vector space. For example, let P of x be 2x squared minus 3x plus 1, and qx, let us take it to be 3 minus x 2x squared. If you add them, so px plus qx will be equal to, so you see it will be the 2x squared and 2x squared will get cancelled, and we end up getting 3x plus 4. Now this is not second degree polynomial. Therefore, so what does this mean? What fails? Addition fails. So we say it is not closed under addition. Therefore, or you can use the symbol. Therefore, this is not a vector space.